Chapter 6, Bending, Part B, Concept of Moment of Inertia. Uh, so far, we just learned about moment of inertia. So if we just want to calculate Ix, so let's say 1, we want to calculate Ix, and that's Ix is integration of y squared dA, and Iy is integration of x squared dA. That's all we know so far about the moment of inertia. And that says why? Because if you want to rotate a sample, an element, upon x about x-axis, you need the dimension of, you mean the length of y. That's why Ix goes by Ix is y squared dA. And if you want to go with the revolution of our sample about y-axis, you need the length of x. That's why I y goes by integration of x squared dA. Let's go a bit deeper to the concept of a moment of inertia. Just consider this is a lake or a water boundary, and this is water level surface, and this, just assume this part as a gate in for a dam and just preventing the water pressure. And the golden plate is the distribution of forces affect the pressure on the gate. So these arrows shows as you dive deeper on the water, you feel more pressure at the top of your head. So that's P gamma, which is related, the pressure is related to the depth and density of your fluid. Mhm. Now let's see what's going on here. When forces are distributed continuously over an area, we are more interested to go by the moment created by those forces. So if you consider the intensity of forces, for example, in water is pressure and some other sample is stress, is almost proportional to the distance, to the length of your traveling downward. So it says pressure is related to gamma times h. And force is dF is PdA, pressure times the area. So far in the nature of force, we do have a h, y, z, whatever you want to call that. So that's one of these, y in our, that's h or y, one of the y in the equation of moment of inertia about, for example, x-axis. And where is the other comes to play? So because we are working with the moment of those forces, so the elemental moment dF, as you can easily see, moment is forces times distance, and that distance can go by y, and that's the second y. So one of the y comes from the pressure formula, and the other y, you can call it y dz whatever, but you should go with the, you should be consistent for both of them. So that's the second y, that's y squared. So one of y's goes by the nature of force and pressure, the other y goes by the moment. So that's Ix is integration of the distance to the x-axis and then y squared dA. Mhm. That was the story of moment of inertia. Let's go a bit deeper to see the mass behind of the concept. So if we want to define a zeroth, first, and second moment of an area, so as you can see here, if you integrate an element of dA, so if you just consider an element part, mhm, and if you want to integrate that for the whole entire area, so that just gives you the area. Integration of dA over area can also called zeroth moment of an area. And that's just area. Mhm. And the other case is when you have something like integration over the area of x dA. We can call that by Sy and Qy, both of them are common. Hibbeler's and Johnson's mechanic of material called that by Qy, but don't just be careful when you like second moment of inertia when you use x, just go by S or Qy. Likewise, when you integrate y over dA, that gives you Sx or Qx. So we call that first moment of an area, and we use very frequently of that in chapter 7 of Hibbeler's book, which is transverse shear. Mhm. We just need to know the effect of shear on a surface. So to observe the vertical effect, that we call that transverse shear, and we are working very frequently with Qy and Qx. Mhm. And the last one is a second moment of an area, mhm, or moment of inertia. So if you want to have a sample, keep it in a revolution about the x-axis, that's ix. And if you want to have another piece, that's ix is equal to y squared dA. And if you want to have your sample in revolution about the uh, y-axis. So that's Iy, that's x squared dA. So that's the moment of inertia or the second moment of an area. You can call it both ways. And what is and so far we just reviewed the formula and also the mass behind of the moment of an area, and we call the second moment of an area moment of inertia. Mhm. Let's review the concept of moment of inertia. Mhm. For a solid circle with the radius of which we already know I is or Ix and Iy, because due to symmetry they are identical to each other. That's a quarter of pi r to the power of 4. And if that's a hollowed shaft or hollowed section with R2 and R1, and then moment of inertia is just a quarter of pi, the outer diameter to the power of 4 minus inner diameter, inner radius, outer radius to the power of 4 minus inner radius to the power of 4, and that's all for a hollowed shaft. And if you have a thin wall tube, then I goes by moment of inertia, it just goes by pi r cubed times t. And the difference between the thin wall tube and hollowed section is that for thin walled we just need the thickness in comparison to radius should be pretty small and negligible, that we can call it a thin walled section. So to derivate this equation for moment of inertia of a uh, involved, we can just make a derivation of moment of inertia of a solid circle. So why is that? Because one can easily say case 1 and 3 are against each other. The very first one has the all mass inside, that the solid circle, and the other one it's almost empty from everything. So it's a narrow strip of thickness, and the middle section is taken out. So you can consider there is no nothing at the middle. So that's a d over dr derivation of the first formula gives you the moment of inertia for the last one. That's a force, the derivation of a force of pi r4. That's 4 times 1 force of pi r cubed, and dr. Dr is also a stand for the thickness. Do you remember I told you the in comparison to r, t is a very small amount. So a derivation of r is almost equal to t. So if you do the math, it just gives you I is equal to pi r square I cube times the thickness. Let's look at to the left hand to the right hand of the table, and that goes by polar moment of inertia. So polar moment of inertia is just Ix plus Iy. So for a solid circle with radius rj, you can also recall it from chapter 5. I can also provide you with the link of them, those material, but it's simply enough that j is a quarter, a half of pi r squared, and for the hollowed shaft, it just says it's a half of pi r2 to the power of 4 minus r1 to the power of 4. And for a thin valve, again, it's a like this time 2 pi r cubed times t. And why is that? Again, you can make a derivation of the very first one, which is a half of pi r4. So it just turns to gives you 2 times pi r cubed times t.